Hello, welcome to our third lecture video. Here I'd like to talk about how we can simulate behaviors through the use of agent-based modeling. Now, what on earth is an agent-based model? Well, it is a computational way of simulating agents interacting with one another and their environment. Did you know that the first agent-based model was done entirely on paper? Well, paper and pen and a couple of coins. It was not created by a computer scientist or an engineer. In fact, it was done entirely by a social scientist by the name of Thomas Schelling. He created the segregation model. Well, let me explain. If you look at any residential area in the United States, you realize that all these residences are divided by races, segregated by races. You have an Asian community, you have a white community, you have an African American community, you have a Hispanic community. Now, whenever we see how the various ethnicities are segregated in the US, we are very inclined to say that this is the result of racism. In fact, this was the prevalent thought in Schelling's time in the 1970s. Thomas Schelling created this model to investigate whether racism was really responsible for the segregation of the races in the residential districts. Now, the point of this lecture video is not to make you an expert in agent-based modeling, but to familiarize you with the thought process involved in creating and using an agent-based model. So, shall we begin? Let's go. In the first place, before we can create an agent-based model, we need to apply abstraction. So we need to determine what are the inputs, outputs, and assumptions needed to create such a model. Let's look at it from the perspective of the agent. Let's focus on the outputs. In the first place, all the agent has to decide is whether to stay in that house or to move out. What then are the inputs? What considerations must an agent have to decide whether to stay or to move out? In the first place, since we are investigating how racism plays a role, we need to inquire, how racist are you as an agent? How many neighbors do you have? And for that matter, how many of your neighbors have the same race as you? Now, what assumptions do we need to make? What kind of simplifying assumptions do we need? One good thing about agent-based models is that we can create an artificial society so simple and different from the real world that we can eliminate a lot of our confounding factors. So what are the confounders that we can eliminate? In the first place, we can eliminate economic differences, right? So let's assume that everyone is of the same economic standing, everyone has the same spending power. Let's also assume that our agents can afford to move house an infinite number of times. And for the sake of this simulation, let's assume that our houses are arranged in a grid-like structure. The only thing that's left to do is our decision process. Let's work out how we would behave in this model in order to derive that algorithm, shall we? Now, let's assume that you belong to the pink race. Power to the pink! And your neighbors are all fellow pink people. In this case, the percentage of people having the same race as you is 100%. Now, let us assume that you have a racism level of 100%. If you are 100% racist and 100% of your neighbors are the same race, of course, you'll be very happy. But what if you're 100% racist, but one of your neighbors is not of the pink race? Let's say you have one neighbor that belongs to the green race. Ugh, green. Reminds me of kale. Ugh, so awful, right? So, that presence of one green person will make you very, very unhappy, and that will cause you to move. Here, as a reminder, we are simplifying the model, so we don't want to consider things like mob violence or anything like that. It's just whether you stay or you move, alright? So, if I'm 100% racist, there's one green person, I will leave the neighborhood. But suppose you now have a racism level of 50%. If you are 50% racist, what this means is that you're okay if half or more than half of your neighborhood has people of the same race. In this case, one of them is a green person. You're okay because you're only 50% racist. What happens if now your neighborhood has 4 green persons? You're still kinda okay, right? What if one of your fellow pink persons move out and is replaced by a green person? Oh, now the percentage of people with the same race as you is 37.5%. Now that is much lower than your racism level. Now you'll be very miserable. You don't want to stay here anymore. Oh, the world is turning green. What am I to do? You'll live for pinker pastures. What pattern can we observe from this? Well, immediately we can see how the percentage of people with the same race as you relates to your level of racism. If the percentage of neighbors with the same race as you is greater or equal to your racism level, you'll stay. Otherwise, you'll move out. And just like that, we have completed the basics of our agent-based model. So let's play this out on paper with coins. For simplicity and not to bore you to death, I will just use a simple 4x4 grid structure. Unfortunately, I don't have pink and green coins. So let's use the $1 coin to represent one race and a 20-cent coin to represent another race. So in a 4x4 grid setting, we will have 16 homes. Let us assume that there is a 90% occupancy rate, in which case there will always be 2 vacant homes and 14 agents. Let's assume that half of the 14 belong to one race and the other half belong to another race. So that's 7 $1 coins and 7 20-cent coins. In this top left-hand corner, this $1 coin has 2 neighbors, a $1 coin neighbor and a 20-cent coin neighbor. That means 50% of the neighbors are the same. At 50% racism level, I will choose to stay. Now, I'll spare you the pain of going through every single agent, so let me just fast forward. Now, notice how after a few iterations, we have arrived at an equilibrium. Notice how all our 20-cent coins are on one side and our $1 coins are on another, even though our racism level is only 50%. Now, the good thing about where we are today is that we have computers and we can do the same simulation without pen, paper, and coins. So here is an agent-based software. It's known as NetLogo. And we can run the same model and see what happens. So here's what happens when we are 30% racist. Isn't it interesting that at 30%, we still get an equilibrium where the races are segregated clearly? 50%, same thing. What happens if we crank up our racism level to the max? 100% racist. Oh, there is no equilibrium. Everyone's constantly unhappy. Everyone's constantly moving. Now, isn't that interesting? Of course, some of you might argue that this model is so far removed from reality. We didn't take into account people's economic status or the prices of homes. But that's missing the point of abstract models. As abstract models, we can create an artificial society, something like a laboratory condition where we can eliminate confounders to isolate just that one variable we wish to investigate. While these models do not immediately translate to the empirical world, they hold theoretical importance. They reveal flaws in the assumptions we make about the empirical world. For example, that racism, high levels of racism leads to segregated residential communities. And they also reveal insights on social dynamics that we ourselves might not have realized, like how a little bit of racism can go very far in shaping society. In the case of Schelling segregation models, knowing there is not high levels of racism that causes segregation is itself a huge change of perspective for policymakers. In fact, they have since changed the way they formulate housing policies. I do hope that this video has familiarized you with the process of developing agent-based models and has helped you to appreciate the use of agent-based models in the social sciences. I strongly encourage you to explore the various ways in which agent-based models are employed in your discipline.